Hello, this is MAT 221, Calculus 1. This is section 3.2 dealing with the shortcuts to the derivative called the product and the quotient rules. So we have some rules so far talking about how to take a derivative using these shortcut rules. So today we'll add two more rules of how to deal with functions that are the product of two functions and functions that are the quotient of two functions. So let's start first by looking at the rule for the product of two functions. So if we have a function that is, we are taking the derivative of a function multiplied by another function. This is the rule that we would use for the product rule. It says, take the first function and don't do anything to it, and then multiply by the derivative of the second function, and then add that to the second function, don't do anything to it, times the derivative of the first function. This is the product rule. Now I'm going to show you why this works. Notice this is not just the product of two derivatives. So the derivative of a product is not just the product of the two derivatives. As it was with the addition rule and the subtraction rule, it does not apply in this case. So the product rule, when you multiply two functions together, the derivative is a little bit more complicated. So often in our textbook they'll say u is one function calling f of x and v is another function called g of x. The product rule is sometimes written like this. It says the derivative of the function u multiplied by the function v is the first function u times the derivative of the second function v plus the second function v multiplied by the derivative of the first function u. This is the notation that the book uses. I like my notation a little bit better, but you can use either notation. Again, notice that the derivative is not just the product of the two derivatives. So let me give you an example. By the way, this is sometimes memorized by this. This is from the textbook. I don't really use that one too much, but this is sometimes how it's memorized. So let's look at the function when we have two polynomial functions, x squared plus 3, which is a quadratic, multiplied by 2x to the third plus 5x. Now when we have polynomial functions, it's actually a lot easier to actually FOIL these two functions, to actually FOIL them through, and then simplify the function and then take the derivative. However, just to demonstrate the product rule here, I'm going to show you both methods. So I'm going to show you. Let's actually distribute here first. If I distribute x squared times 2x to the third, I get 2x to the fifth. X squared times 5x, we get 5x to the third. 3 times 2x cubed gives us 6x cubed. And 3 plus times 5x equals 15x. So here I just FOILed or did a double distribution here of the two binomials. Now, if we took the derivative term by term, the derivative should be simplified 10x to the fourth plus 33x squared plus 15, using all of our rules that we have up to this point. This should be the derivative of this function. Now notice if you just took the derivative of the first function, which was 2x, and just took the derivative of the second function, which is 6x squared plus 5, and then multiplied them together, you would not get the correct result. So again, when we have the product of two functions, it is not just the derivative of each multiplied together. That is wrong. We have to use this rule. So here's the rule. Let's apply the product rule. The first function, don't do anything to it, times the derivative of the second function plus the second function, don't do anything to it, times the derivative of the first function. Now, doing a little bit more algebra here, FOILing and simplifying like terms, you can see that we get the same derivative that we should. Now again, if we are given two polynomial functions, it's easier to do it this first way. Just FOIL first, then take the derivative. However, if we are not given two polynomial functions, which is the most part what happens in our upper level mathematics, we would need to use the product rule. So let's try some examples. Notice here I have a function multiplied by a function. I have a quadratic multiplied by e to the x, an exponential. I have to apply the product rule. The product rule says the first function, don't do anything to it, times the derivative of the second. Now in this case, the derivative of e to the x just happens to be itself, plus the second function, don't do anything to it, times the derivative of the first. Now, I didn't simplify this at all. We could leave it just like this. WebAssign will actually take this as a correct answer. We could, if we wanted to, actually take out a GCF, a common GCF here, and simplify it a little bit. But for right now, let's just apply the rule. Let's try another one. Notice I have a polynomial function multiplied by an exponential function. I have a function times a function. Product rule says the first function, don't do anything to it, times the derivative of the second function, that's right, times the derivative of the second function, plus the second function, which is e to the x, times the derivative of the first. Now again, I could manipulate this a little bit, take out a common factor of e to the x, and then be left with x to the third plus 3x squared plus 1. But for the just having to apply the rule right now, let's just leave this alone. Let's try another one. Remember a radical function, right? We have a new algebraic function here and an exponential function here. They're being multiplied by each other. See the multiplication sign. Remember, x to the 1/2 is equivalent to the square root of x. So let's take our derivative. It would be the first function, don't do anything to it, times the derivative of the second function, which is itself times the natural log of its base. That's the exponential rule. Plus the second function, don't do anything to it, times the derivative of the first, which would be 2x minus 1/2 x to the negative 1/2. Remember, x to the 1/2, the 1/2 comes to the front, subtracting 1 from the exponent. Again, I could pull out a GCF. It has a GCF in this case of 3 to the x is the GCF in this case, but for the purposes of just learning the rule, let's leave this alone and not do the continued algebra here. Again, we have a function times a function. Here's the derivative. The derivative says the first times the derivative of the second plus the second times the derivative of the first. All right, there's the product rule. Next, let's look at the quotient rule. The quotient rule is used when we have a function divided by a function. So notice if I have a function divided by a function, the rule says the denominator multiplied by the derivative of the numerator minus the numerator, again, don't do anything to it, times the derivative of the denominator over the denominator squared. Now, a long time ago when I took calculus, I had a teacher, Mr. Murdo, who taught us this by singing to us. And he said, when you sing, you always start low. So he used to sing this song to us. Excuse me for my bad singing, but he would sing, the derivative of the quotient rule is low d high minus high d low all over low low. It was his way to keep us to remember, a way to help us remember the way that the quotient rule is found. Now notice this is a lot like the product rule, except for it's a fraction, and it has a subtraction. So the key thing here is with addition, it didn't matter with the product rule which one we did first. We could do the derivative of the second function first or the first, and we would still get the same answer. Here it matters what we do first. So he always says when we sing, we start low. So we start with the denominator, then take the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So let's look at an example. Again, let's put it into this formula. It would be the denominator, x squared plus 3, times the derivative of the numerator, which would be 6x squared plus 5, minus the numerator, which is 2x to the third plus 5x, times the derivative of the denominator, which would be 2x, all over the denominator, x squared plus 3, quantity squared. So there's our derivative. Now I'm not going to simplify this one, but we will do some simplifications of the next couple. Find the derivative. Notice we have low d high minus high d low over low squared. Denominator, derivative of the numerator, minus numerator, derivative of the denominator over the denominator squared. Simplifying the numerator, we get negative 2 over x minus 1 squared. By the way, we hardly ever, we leave that FOIL or that factored form in the bottom. We hardly ever actually FOIL that bottom out, but we usually simplify the numerator. Let's do another one. Again, we see low d high minus high d low over low squared. Simplifying a little bit of my numerator, I pulled out a GCF of 3 to the x and x squared. There's my simplified, when I can then cancel x squared and 2 of these x's in the bottom. Again, let's try the quotient rule. Low d high minus high d low all over low squared. And a little bit of algebra, we simplify. Sometimes we work just with numerical values. For instance, say a function y is the product of two functions that we call u and v, and we wanted to find the derivative of this function at 2. What we would do is, if we had the given information, notice I don't have the actual function, but I have some information about this function. I can then use the product rule here, if I know that I have the two functions, u and v are both functions. And using the product rule, it is the first times the derivative of the second plus the second times the derivative of the first. And if I wanted to know what the derivative here was at 2, I would put all these values in at 2. And I know the value of u at 2, and v at 2, and v prime at 2, and so forth. So putting all of these values in, I know u at 2 is 3, v prime at 2 is 2, v at 2 was equal to 1, and u prime at 2 is equal to negative 4. So putting in those values and then just doing a little bit of addition, I can find the slope of the curve at that point if I'm given this numerical information.